This is a quick video to show how to do a t-test in Excel. Here is a quick example where we're testing if decellularized blood vessels have the same properties, in this case ultimate tensile strength UTS, as native blood vessels. So assuming these have properties have a normal distribution, you can use the t-test. So we're going to do that. And first thing we want to do is do our descriptive statistics, so we can calculate the mean, which in Excel is average of each column. And I can copy that over here, paste it there, and the standard deviation, a measure of the variability of the data. Proper significant figures. And so they have pretty close means to each other, 1800 kilopascals and 1650 kilopascals, and similar standard deviations also. I like to calculate the coefficient of variation for the percentage difference, percentage variation, and that's equal to the standard deviation divided by the mean. And again, these groups are pretty quick. So now I want to do a t-test between them. So assuming these are 5 independent native and 5 independent decellularized, we would do a non-paired t-test. And to do that, we say equals t-test. And then it has a series of groups, a series of components. And so we first put our first array in there, and then comma, and our second array, comma. The number of tails, I'm going to put 2 because I'm not presuming that it's either higher or lower. My hypothesis is that there is no difference. So I'm using a 2-tailed distribution. And then the final one is paired or unpaired. You can either select equal variance or unequal variance. Equal variance will give you a little higher statistical, or a little lower p-value, let's put it that way. These are very close. You can see the standard deviations are very close. So I'll use equal variance first. So I'll put a 2 in there, and then parentheses. And so you see here that the p-value is 0.076, which in normal scientific circles, if it's not below 0.05, then it is not considered statistically significant. Now we can do that same thing with, I'll copy it and I'll paste it here. And instead of equal variance, I'll use unequal variance. And you can say it's very, very similar because these were similar to start with. Now the big difference is going to come, so this is equal. This is P equals, and this is with equal, and this is with, and then the big difference here will come when we pair it. So that is the proper analysis if these are not before and after or somehow linked samples. But if we instead knew that the native sample was then tested and then it was decellularized and tested again, let's say we had a tissue in your blood vessel and we cut it in half and we tested 1/2 native and then we decellularized it and tested the other half, and it goes down a little bit, and you can see the difference is I'm going to copy that. So now you can see that all the differences are positive. It never got stronger with decellularization. I subtracted native to decellularized from native, and they were pretty similar except for this 51. So pairing them and saying, really test what is the difference between them. So now we put in the array 1, comma, array 2, comma, tails, again 2. I'm not saying whether it's larger or smaller. And then paired 1. And now when I do that, it is much lower than 0.05. So a paired t-test gives you you're much more likely, if you have consistent differences, to get statistical significance. It also gives you a much higher power, which I don't have time to talk to right in this video. I'll do a different video for that. But you can only do paired when there's actually a way of pairing the samples, such as before or after, or two samples from the same, two specimens from the same sample.